Hello friends, today we will study about logic families. Okay, so logic families. Now, logic families we used to design some gates, right? If using some family, if I'm able to design NAND gate or NOR gate, then it will be very helpful. And using that NAND gate and NOR gate, I can design any circuit because NAND and NOR gate are universal gates, right? So there are various families by which I can make such logics. So we will be seeing that, and also we'll look what are the advantages and disadvantages of this families. Okay. Before going to families, I will design a circuit and we will analyze it. Okay. So the circuit goes like this. Right, this is a circuit, and let's analyze this circuit. Okay, so let's take A, B, Y. So as there are two inputs, A and B are inputs and Y is the output. As there are two inputs, so total 4 combinations are possible, that is 0 0 0 1 1 0 1 1, where 0 means low and 1 means high. Now if both are 0, so this diode will be on as VCC is connected to positive side and lower voltage is connected to negative side. So this both diodes will be on, and then this both diodes are on. This Y will be directly connected to 0. So this will be 0. If again A is on, that is 0 voltage is given to A side. So this again this will be on. So again Y will be 0. Similarly, this is on, then again Y equal to 0. Now if both are 1 1, that means these both diodes are off and no current flows through this, so no voltage drop is there across R. So Y will become VCC, which is logic high, so it will be 1. So which type of gate is this? This is AND gate, right? Now this circuit gives me a logic of AND gate, but using AND gate I can't design all the circuits, right? I need to have either NAND gate or NOR gate. So using NAND and NOR I can design every circuit because NAND and NOR are universal gates. So again I can use this thing, but AND plus NOT will give me NAND. Right, if I pass the output of AND gate through an inverter, the output of the inverter will give me NAND gate. This is inverter, right? So let's see the circuit which will exhibit a NAND gate. So let's draw the circuit for NAND gate. Okay, so this is again VCC, R, A, B, two inputs. This is the output, and this output is AND gate, right? I will pass it through a well-known inverter. And this you can take it as R1, and this you can take it as R2, and this is ground, and I will take the output voltage here. So now I say that output of this is AND and it is passed through an inverter, so why should be NAND gate? Now looking to this circuit is good, means though this circuit looks good that AND gate passes through inverter gives me NAND gate, but does this circuit really works? Let's analyze. Okay, now assume A and B to be low. Correct. If A and B is low, for Y to be a NAND gate, it should be high, right? When any of the input is low, Y should be high. So if A and B is low, so in logic circuits we usually take low voltage as 0.2 volts, right? If this is like 0.2 volts and the voltage, so 0.2 volts means this diode is on, right? And if this diode is on, this voltage drop across this diode will be 0.7 volt and this potential will become 0.9 volt. Now for this to be logic high, this transistor should be in cutoff, but when there is 0.9 volt here, this transistor will go to active. Why? Because there is one diode, right? And this diode, there is one diode, and this diode should be in the reverse bias for this transistor to be in cutoff. But because of this 0.9 volt, 0.7 volt will drop across this and this diode will come in forward bias, and because of this transistor will go to saturation and hence this is not working as a NAND gate. So this circuit actually does not work. Now what I can do, I can simply replace R2 by an diode. Okay, let's see the circuit. What I can do is I can replace this by a diode. Now take A and B, A or B or both to be low. So if suppose B is 0.2 volt, this diode will be on, here potential will be 0.9 volt. Now this 0.9 volt will divide equally between this diode and a diode across this. Now we know that the base to emitter voltage is 0.7 volt and diode cutting voltage is also 0.7 volt, right? Now if I have 0.9 volt, this the voltage can never be 0.7 volt between these two. It will divide equally between these two diodes, so it will never reach 0.7 volt because I don't have 0.9 volt. For both this diode to conduct, I should at least have here 1.4 volts, right? So this diode is reverse bias and hence this circuit goes to cutoff and then Y will be logic high, right? So for this circuit I will make the truth table. Maybe Y 0 0 0 1 1 0 1 1. So if 0 0 both are on, here the voltage will come 0.9 volt as this transistor will not conduct and hence this Y will be logic high. So this will be 1. Same with this, same with this. If 1 1 means both the diodes are off, this voltage will come, some voltage will come this side which will be way more than 1.4 volt and this diode will be on and hence this transistor goes to saturation and then Y becomes logic low, that is 0.2 volts, that is VCE sat, that is equal to 0.2 volts and that can be considered as logic low. So this will be 0. So this is a NAND gate. Now as we discussed, this circuit is a NAND gate. So this is a NAND gate. Using this gate I can design any other circuit. Right now there are some disadvantages of this circuit that we have to discuss. First of all, there are diodes and transistor. So this type of logic families are called as diode, transistor, logic family. DTL. Okay, because there are diodes and transistors, so this is called as diode, transistor, logic family. So what are the disadvantages of this circuit? Now assume that B is A was 1 only and B was changing from 1 to 0. There was a transition of B from 1 to 0. Okay, now as soon as 1 becomes 0, this potential becomes 0.9 volt and this transistor should go to cutoff. But when this was 1, so this was in saturation, means Y should go from low to high, that is saturation to cutoff. Now this transistor to go to cutoff, the whole charge which is stored in a base should get removed, right? Then only this transistor will go to cutoff. So whatever the charge which is stored in base, it should come out. But as we know, diode does not allow the current in a reverse direction. So actually there is no path for the charge which is built up in base to get out. So actually this circuit does not work very fast. It takes a lot of time to take the charge away from this side. So to increase the speed or to remove this charge, what I can do, I can have a path here using a resistance, let's say RB, and I can have some negative potential here. So this point will be 0.7 volt and the charge which is stored here can get removed through this capacitor, this resistance, right? The charge which is stored in base will remove through this resistance. Now again, this circuit also has a disadvantage. It has 2 power supplies. Now in a single circuit using 2 power supplies is not advisable. So we should make something else which will help me in removing the base charge. Okay, now we will study the second logic family, that is transistor logic. Now in transistor logic, what I did, I will remove this diode and this diode, and I will make transistors instead of diodes. So let's make the circuit for this. This is VCC R, and I will use a multi-emitter transistor. This is A, this is B, and this is VCC, and this is R, and this is output Y. This is also the circuit diagram for a NAND gate. Now these 2 diodes are diode across this and diode across this, and this diode is diode across this. So this circuit get replaced by this. Now what is the advantage of this circuit? This circuit is far better than this. Let's discuss how. Now see, if A and B are low, right, the current which will come from here will totally flow through this path, and there is no current flowing through this part. And if there is no current flowing through this part, transistor will be cut off and then Y will be high. And if both inputs are 1, the current will flow this side, and this transistor goes to saturation, and Y will be logic 0. So this is a NAND gate. Right, now see, when this transistor goes from saturation to cutoff, there is a the current can flow here. Why? Because usually the collector current allows the current to flow in this direction, right? Collector current usually flow in this direction, right? So when this goes through, when this wire changes from saturation to cutoff, the charge which is built here will have a path to flow through this, because again this is the collector of a transistor, and through collector it allows to the charge to go in this direction. So this is like far better circuit than this. Now, as we discussed, this circuit is a NAND gate, and this is better than diode transistor logic. But this circuit also has some disadvantage. Let's see that. Now assume there is some capacitive load here. This is CL. This capacitive load can be from the next stage. So we have some capacitive load. Now when the output goes from saturation to cutoff, right? When this transistor goes from saturation to cutoff, this wire should get charged. This capacitor should get charged to VCC. That means the current should flow like this. Now a large current to flow through this, my R should be low, right? To have a large current flowing through this, so that capacitor gets charged up quickly, a large current should flow from this side, and hence this R should be low. Now if I take R to be low, and when this output goes from cutoff to saturation, a large current will flow like this. Why? Because R is low, so large current will be flowing when it goes from cutoff to saturation. In saturation, my transistor will allow current to flow, and because of the large current, the power dissipation across the transistor will increase. So actually I have two conditions. When sat to cutoff, R should be low, and cutoff to sat, R should be high. Now we can't have two values of R, right? So we need an active device to exhibit this. So we need a active load, right? So in next lecture we will see some advanced version of transistor logic using an active load, which will eliminate these two conditions, and that will be a better circuit as compared to this.